Thank you. So good afternoon and welcome to my session about getting from IP ID to a device ID in KASLR bypass. This research was done jointly with Professor Benny Pincus from the Ilan University. So this is all about user or more explicit, more accurately device tracking. Why do we need that? Well, we don't really need that. It's mostly done for real-time targeted marketing, which we all love to hate. Actually, John Wilander, one of the keynote speakers yesterday, called it nicely cross-site tracking. And of course, we have campaign measurement. On a more positive side, we have fraud detection and protection against account hijacking and various many other reasons, good or bad, for device tracking. So we're going to use the IP ID header for device tracking. And just to remind you all very quickly what IP ID is, it's a 16-bit IP header field used for packet fragmentation and defragmentation. As such, it should not repeat too closely within an interval of minutes, ideally, for the same source IP address and destination IP address. And following 20 plus years of security research, it should also be not predictable. And the implementation of choice for Windows and for Linux and Android stateless protocols like UDP and ICMP follows the same approach, the same concept, having a large area of counters, several thousand counters, having a hash function from the source IP address and destination IP address and some secret key into this array, calculating an index using this hash value, incrementing the counter, and Linux and Android had this extra twist of adding some extra randomness based on time, and then using the result, and in this case Windows has an extra twist of adding another hash value of, again, the source IP address, destination IP address, and another key. So you can see that the structure of the IP ID generation algorithm in Windows and in Linux and Android is pretty much similar. Of course, there are some specific deviations for each operating system. And we are going to exploit this structure for generating a device ID. The idea of our attack is that, or the general setup of our attack is that attacker generates a tracking HTML snippet that contains some JavaScript code, and this snippet can be embedded in practically in any site, hence cross-site tracking. This snippet will calculate this device ID. And the snippet works by forcing the browser to connect to multiple attacker-controlled IP addresses. The attacker then collects the IP ID for the traffic generated to its IP addresses. And we show how an attacker can calculate a device ID based on that. This device ID will remain unchanged across browsers, network switches, VPNs, and privacy mode, and therefore it can be used to track the user, or more accurately, the device. And the lovely thing is, of course, is that each snippet or each site can use a different set of destination IP addresses. In other words, you cannot use a specific set of IP addresses in one site to say, aha, that other site is also using the same tracking mechanism. So we do that by cryptanalyzing the IP ID generation algorithm, both for Windows and for Linux/Android. Our attack requires, as I mentioned earlier, sending traffic to multiple attacker-controlled IP addresses and collecting the IP IDs of those packets. And then the interesting part is that we are using collisions of that hash function I mentioned earlier, that hash function that takes the source IP address, destination IP address, and turns a key and turns it into an index into the area of counters. We're going to use collisions of this hash function, which results in packets for different IP addresses having their IP ID generated by the same counter in different times. And we use that to find the algorithm key either in full or in part. This key will effectively be 32 bits to 48 bits depending on the use case. And this key, since this key is essentially unique per device up to the birthday paradox, it will serve as the device ID practically. The nice thing about this key is that it is only regenerated at startup, and Even nicer with Windows is that this key is only generated at restart, which is not equal shutdown plus start. So if you do a shutdown plus start, the key is not regenerated. It's the same key from the previous session. Obviously, since it's IP, at the IP level, it's the same key for all the browsers, including the privacy mode, and it's the same key for all networks, including many VPNs. And of course, since it's just a one key, it's invariant with respect to the set of destination IP addresses. So let's look at the Windows implementation. We call beta the counter array, which is of size a bit more than 8,000 buckets. And the IP ID generation algorithm, as we reverse engineer it from the TCP/IP/sys Windows driver, calculates the index based only on the class B network of the destination IP address, which will come very handy in a moment. And then it adds it calculates some it adds some value k1 exclusive or tk blah blah blah, increments the counter and uses the value it calculated earlier as the IP ID. And this T function over there is the Toplitz hash function, which is a bilinear function, which again comes in very, very handy because it's extremely weak. So we attack Windows in two phases. In phase one, we know that since the index I into the area of buckets depends only on the class B of the network destination IP address, and since only the 15 least significant bits of the counter are used, we take several, like 6 IP addresses in the same class B. The attacker needs to set up those addresses in the same class B. It's quite trivial. I did it in Azure very easily. And doing some crypto math here, we get up to the situation wherein at the left-hand side we have quantity that we can calculate because we guess the beta of I, that's those 15 bits that we enumerate over, and then we know the IP ID at position P, we know P, and so we can calculate the left-hand side. At the right-hand side, since we know the IP addresses, we know the exclusive OR value. So the only thing that remains unknown is the K at the right-hand side. Hence, we have 15 bits of 15 equations over GF2 on bits of K. And it's naively speaking, I'd say it's enough to have 2 such sets of equations to calculate 30 bits of K. In practice, we need some more. Details are, of course, in the paper. But at the end of the day, we get 30 bits of K, and with that we move to the second phase, where we take additional pairs of IP addresses in additional class Bs. And again, we use some quantity X that we calculate we can calculate from phase 1 and arrive at the 2 equations, one for j equals 0, first packet, and one for j equals 1, the second packet of a pair. And since they are both equal to the right-hand side being the initial value of this arbitrary counter that is used for the pair, we have another 15 bits elimination power from each such pair for this enumeration over additional 16 bits of K. Altogether, at the end of the day, after phase 2, we get theoretically 46 bits of K, practically somewhere between 41 to 45. Again, this is all explained in the paper. And this serves us as the device ID for Windows. So a quantity of 41 to 45 bits that is generated at boot is the device ID for Windows, and I explained right now how to calculate that. Moving to Linux and Android, and I want to do first a quick refresher of what KASLR is. So KASLR is kernel address space layout randomization. It's a specific use case for address space layout randomization, ASLR. And ASLR is used to mitigate ROP attacks. ROP is return-oriented programming. It's also used to deflect JOP attacks and similar attacks. And the ROP attack is based on chaining small snippets of code that are called ROP gadgets to form a malicious program. Now, these ROP gadgets need to reside, are pieces of code that the attacker knows where to locate in the memory of the target process. So, in order to mitigate such attack, ASLR was invented, and ASLR simply randomizes the image load address of modules, programs, and other useful pieces of code to prevent the attacker from knowing the locations of those ROP gadgets. KASLR obviously does the same at the kernel level, and at a minimum, it randomizes the kernel image load address. And I want to stress that enumeration of the random offset is quite not applicable at the kernel level, because each wrong guess will get the operating system to crash or freeze. This is, of course, very invasive, and it's time consuming, takes time for the operating system to load itself up, so quite impractical. The attacker really needs to know the offset of the random offset of the KASLR in order to mount a ROP attack. So having a KASLR bypass means is equals to knowing the kernel image address offset. And this will be useful in a moment. So the IPID generation algorithm for Linux and Android, only for stateless protocols like UDP and ICMP. The algorithm simply uses a keyed hash over the destination IP address, the source IP address, a protocol which is 17 for UDP. It's constant part of the IP RFC. And something and G of net, which I will touch in a moment. And then this is the index to the array. We take the bucket, take the counter value in that bucket. We add 1 to it, and we also add a random quantity between 0 and the time elapsed between now and the previous time this bucket was updated. And we use that for the IP ID as well. And we have, in this case, over 2,000 counters, and this timer is the GFIS timer, which is 100 hertz, 250 hertz, or 300 hertz clock counter initialized at boot. What is net? Net is actually a kernel address of a static kernel variable. So it has its offset known from, it has a known offset from the kernel image load address up to, of course, KASLR. It's, of course, build dependent, but we assume that the attacker can figure out the exact build. It's pretty easy, at least for many Linux and Android models. And G is just a function that shifts all those random KASLR bits, offset bits, into the low 32 bits of the result. So the result is 32 bits, including that includes bits from the KASLR offset. And the underlying issue in Linux and Android appears to be the fact that they do use a crypto, not a phenomenal crypto. This hash function is not overly strong, but at least it has some cryptographic value as opposed to a linear function, for example. But it uses so with a ridiculously small key space of 32 bits. So the attack goes as following. It's a bit simplified version. In the browser, we force the browser, the snippet forces the browser to send a burst of, say, 400 UDP packets, one to each IP address that the attacker controls. So the attacker needs to control like 400 IP addresses. It's doable. It's not within our budget, but it's doable. Now, what happens when two such IP addresses have a collision so that they have the same index into the counter array? This means that the time elapsed between those two calculations of IP ID is pretty small, because we are in a burst, and empirically we are talking about less than 0.6 seconds. So even with the worst case clock at 300 hertz, we are talking about less than 180. So the difference in IP ID values in between those such packets would be less than 180. This is as opposed to the average 32,000 on something that you get for two random IP addresses and two random IP IDs. So obviously it's easy to find candidates for such bucket collisions, and we do that. We collect pairs of IP addresses that obey this delta in IP ID less than 180. And of course, there will be false positive, but we will have a large body of true positives. So then we enumerate over the 32-bit key, and if we have newer Android kernels and Linux kernels, you also need to enumerate over the KASLR offset, which is 9 bits for Linux, and 16 bits for Android. And for each key, we count the number of real bucket collisions inside our candidate pool, and we calculated in the paper a good threshold of 11. So if the number of true positives is above 11, we found the good keys and the good offset. Now this can be CPU intensive, especially in the case of newer Androids where we have 48 bits to enumerate, but the upside is that we also find the KASLR offset, and therefore we have a KASLR bypass. And so this key, 32 bits to 48 bits, depending on the Android kernel version, serves in the Linux and Android as the device ID. So of course we we notified Microsoft and the Linux Foundation. Microsoft fixed in April 2019 and issued this CVE. Linux fixed in April-May timeframe. They also had us contribute a fix to the older 3x branches, and we issued 2 CVEs, and so you can relax, everything is now fixed. And the conclusions we have from this research are that the security and privacy are a concern even when generating seemingly non-security data such as this code-forsaken IP header. We recommend, of course, using industrial strength crypto as opposed to linear functions. We recommend using adequate sized key rather than 32 bits. And of course, we recommend not using sensitive data such as kernel addresses as part of your key. And that's it. Thank you very much.
Do we have any questions for our speaker? I have one part that I didn't get, which is for the Linux and Android attacks, you require UDP packets to be sent. So how does the attacker get the victim to send UDP packets to it?
Excellent question, and actually it puzzled us a bit, and we found that you can do that actually with 2 methods. We used in our research stun packets over WebRTC, which you can emit through the some HTML5 APIs from JavaScript. You can do that. Actually, and the nice thing about it is that it's bursty. But you can also, in Google Chrome, you can also use gquick because it's over UDP. But we didn't bother with that.
And then for both attacks on Windows and Linux and Android, how much time are we talking about in order to?
Dwell time in the snippet or calculation time?
World time to actually get the key broken.
So calculation time, like attack time.
Yeah.
So in Windows we actually have it like in sub-second, and in Linux, if we're talking about 32-bit enumeration, you can do it if good hardware, you can do it in seconds. If I did break a 41-bit Linux key with 32 bits plus 9 bits of offset, 12 hours run of a very average machine, let's say. Of course, it gets more. It gets less practical with 48 bits, but still, if you have enough horsepower, you can do that as well.
Okay, let's thank our speaker again. Thank you.